This is how we define the group algebra. We take the group elements and say they form a basis of some vector space. So we take linear combinations of group elements, and these are the elements of our group algebra or group ring. In this context, we often find it convenient to enumerate the group elements from 1 to the order of the group. And now we make it an algebra by also introducing a multiplication rule. So we take two elements of our group algebra, say Q and R, each a linear combination of the group elements, and then we multiply them like this here. And now notice that here's a product of two group elements, and since it's a group, the result is again a group element. So this means this thing here, is again in the group algebra because it's a linear combination of group elements. And when I said we make it a vector space, then I have to say how we define addition of elements in A of G and multiplication with scalars, and we do this component wise. So if we add Q and R, we add the coefficients of Q and R of the group elements, and we can also multiply with C numbers like this. And as a vector space, since the group elements are the basis for this vector space has dimension order of the group. So that's the dimension of the group algebra. Now there's one more remark I want to make. If we have a representation of the group gamma here, then this also defines a representation of the group algebra in the following way. We say gamma of a group algebra element is just a linear combination of the representation matrices of the group elements, and this is a representation of the algebra in the sense that now we have these rules here for addition or linear combinations here, linear combinations of group algebra elements and products. So sums and multiplication with scalars become linear combinations of the representation matrices, and we also have that gamma of a product is just the product of the representation matrices.